Welcome to this February First Fridays, and I'm very excited about this particular topic because um, I've always violinists and bow makers know about the importance of the center of mass or the balance point of bows, but I've always thought that the moment of inertia of the bows had to be important, and so um, now finally. Victor Castrillo has done his PhD research on this very topic, and he's going to tell us what he has found. So, Victor?
Thank you very much, Pan. Thank you all for being here. So yes, I'm going to talk about my investigation on the influence of bow mass distribution on the perception and the performance of violinists, which is a topic that I covered during my PhD here at Sorbonne University under the supervision of Claudia Fritz. So well, let me start by defining mass distribution, not defining, but saying that along with camber, bow makers can adjust this property, the mass distribution of the bow, even after the construction of the bow. So it is a parameter to which
This is
bow
about
makers can.
bows and how bows affect.
Yeah. Oh, sorry. So bow makers can fine-tune this parameter to the player's preferences. And how may they do so? Well, by simply changing the density or the weight of different parts of the bow. For example, the tip plate, which can be made out of plastic, ivory, or silver. But also at the bottom part of the bow, the winding has may be made out of different materials. For example, some types of light fabrics, up to more heavier alternatives. For example, of silver. But also at the frog, we can have different materials for the frog, and also for the button, and even different morphologies for the frog. So there is a certain leeway in adjusting the bow mass distribution even after it's been built, and that is thanks to the use of different materials. But what are we changing when we modify the weight of these elements? Specifically, by adjusting this mass distribution, while keeping the total mass of the bow constant, we can modify the center of mass, which I think it's a parameter that most of you may be used to it. It's if you look to my, here I have a bow. It's normally the balance point where when we hold the bow like this, it stays at the same. It doesn't fall off. So here I give the formal definition of this center of mass position, which is the weight average position of all the particles of the system. But there is also, as Pan was saying before, the moment of inertia, which is a measure of an object's resistance to a rotational motion about a specific axis. So it is usually represented by the ballet dancer or ice skater that increases her angular momentum or his angular velocity when the arms are closer to the body, because this moment of inertia is a function of the mass of the particles of the system times the distance to this rotation axis squared. So, well, I'm really going to focus on the moment of inertia. So we have to first define about which specific axis does the bow rotate, because it's not fixed to any axis when a violinist is playing. So in literature, we have a lot of, and from the point of view of the player that is holding the bow will rotate around the thumb position. So here I have different pictures of how the bow is held, and how this vertical rotation of the bow is made with a balance of both the little finger here to lift the bow from the strings, and the index finger to press the bow on the string. So this vertical rotation is made around the axis that passes through the position of the thumb. So this is the axis about which we are going to calculate the moment of inertia. And most importantly, how do we measure these mechanical properties? Well, for the center of mass, it's quite straightforward. We just have to check where does the bow keep its balance when we hold it from as pictured here in this figure. And for the moment of inertia, we can estimate it by letting the bow oscillate freely around the specific axis that I was talking about. So if we simply take a clamp and hold it from this position, the bow will oscillate proportionally at a pace inversely proportional to the moment of inertia. So we can, for example, measure how much time does it take for the bow to make 10 oscillations or so, and then calculate the period. And with this period, we can estimate the moment of inertia around about this axis with the formula that I give here. Okay, so we are going to focus on how these variations in these mechanical properties that are given by mass distribution affect both the performance and the perception of the violinist. So we estimate that the influence of mass distribution of the bow is not very big to the left hand performance. So we will simplify our system by taking this hand apart. And our objective is to see how, when we change or modify the mass distribution of the bow, the violinist, how does the violinist change his way of playing, his performance or her performance, and if there are changes in the perception of the bow qualities. And to do so, we used an experimental violin bow, which was designed and built by bow maker Duilio Spalletta. And here I show different stages of the construction of this particular stick. The characteristics of this bow is that, well, since our focus was on variations in mass distribution, Duilio came up with the idea of designing this very light Pernambuco bow, which is 52.6 grams when the standard is 60 grams, and came up with the idea also of using a small magnetized magnets that could be positioned at different parts where he put different small pieces of magnetized nickel. I think it was nickel. This allows for an easy modification of the mass distribution while keeping a total mass of the bow. And we can reach the standard weight of the bow of around 60 grams with different mass distributions. Since we are going to do these perceptual studies, we also covered these magnets with light pieces of paper and foam, so that we avoid any kind of visual biases. Okay, so with this bow, we managed to design, along with Amélie Picard during her internship, 5 mass distribution that shared all of them the same total mass of the bow. So all of them are different mass distributions, but with the same total bow mass. What we did is, with these 5 mass distributions, we could have different moment of inertia with the same total mass and with the same center of mass position. So we could change these to specific mechanical properties, the moment of inertia and the center of mass position measured from the frog. So for example, here in the diagram, we have bows A, B, and C I will refer throughout this presentation to these bows as if they were different bows, even if we can discuss if they're the same bow if we are changing the mass distribution, but I just want to make it clear that it's always the same stick to which different combinations of magnets at different positions have been added. So we have 5 bows. A, B, C will be bows that are changing in the moment of inertia, but they have all the same total mass and the same center of mass position. And bows A, D, and E will have more or less the same moment of inertia and different positions of the center of mass. And how do these mass distributions and the properties of these bows fall within the normal values? We calculated the mean and the standard deviation of a set of 14 modern bows of musicians that came to do the experiment with us. And we calculated the average center of mass position, the average mass, and the average moment of inertia. And we saw that our designed mass distributions were for both A, B, and D, the values of the center of mass and the moment of inertia fell within the normal values, let's say, and both C and E were outliers in just one parameter. In the case of bow C, it's an outlier in terms of moment of inertia, and in the case of bow E, it's an outlier in terms of the position of the center of mass. Okay, so today I will show you, I will present you 2 experiments that we did with these musicians and the results that came with them. So first I will present this study on the perception of violin bow mass distribution, and then I will present a study on the influence of the bow moment of inertia on the bowing parameters when performing bouncing strokes like spiccato or sautillé. So let me first start with the study on the perception of violin mass distribution and on the hypothesis that we may have on how these mechanical properties may affect the violin, the perception of the bow from the point of view of the violin. So the center of mass, we made this hypothesis based on 2 situations: when holding the bow horizontally and when playing with the bow. So first, when we just hold the bow horizontally, like when we are going to attack one string in pianissimo at the tip, there is this, we have to do this to hold the bow horizontally, for example. And we see that the closer the center of mass to the frog, the lighter it will be perceived because of the moment of force of the weight. Since the center of mass is closer to the axis of rotation of the bow, this moment will be lower. And the effort to keep it horizontal will be also lower. And on the other side, when playing, there will be differences when playing horizontally, differences in the necessary finger forces to exert a specific force on the string. So, for example, if we want to exert here at the left a force, specific force FB at this specific position of the bow, the closest the center of mass to the frog, the highest would be the necessary index finger force to exert this force. So we see that there will be a change in the balance of these 2 finger forces during a horizontal bow stroke. And on the other side, the moment of inertia, we also base our hypothesis in 2 cases: when we are holding the bow, not playing with it, and we are shaking it in the air, so forcing rotations of the bow around this specific axis. since I already explained before, the higher the moment of inertia, the higher will be the effort to make it rotate or to shake it. So if we have a bow with a higher moment of inertia, it will be much harder to perform some kind of strokes that require a rotation about this axis. And there's also another consequence when playing. The higher the moment of inertia, the lower the bouncing frequency in contact with the string. That is, when we have the bow which is in contact with the string, there are vibrational modes that make it vibrate. So for the first mode, for example, the higher the moment of inertia, the slower it will be vibrating in contact with this string. Okay, so we're going to do perceptual measurement text with people, and we have this the problem of sample size. So the work of I will say every bow maker is to make individualized research to achieve what the violinist or the client wants for a specific bow. And the problem with an individualized study is that there is a low reproducibility. So we scientists usually require a high reproducibility to be called a scientist. It's what a scientific method establishes. So we would need to have a higher number of people so that the individual variations are averaged out, and we will have a higher reproducibility, so that if we do this study again with another with a different set of violinists, we would have a higher probability of obtaining the same results. So we chose this approach, and with all these people that we wanted to invite to our laboratory, we did 2 types of perceptual tests with both professional and amateur musicians. First, we did discrimination tests, which are experiments to verify whose objective is to verify if musicians can detect small or large changes in both properties that I mentioned before, the center of mass and the moment of inertia, to see to what extent they are sensitive to variations in these properties. And then we performed a free evaluation test, this time only with big changes of those properties. You remember that those outliers, both C and E, which are an outlier in the moment of inertia and the center of mass, we only considered these both to analyze how they described these changes. So I propose you an example in order to understand what the method that we used. So let's evaluate or estimate the weight of a specific bow without knowing how much how heavy it is. We know, because we can weight it, that it weighs 60 grams, but we propose our participants to evaluate its weight. It's an example, so it's help me with it. So the first musician comes and says that this bow, it weighs 59 grams. So we say, okay, this one, musician 1 says that it's 59 grams. Then musician 2 takes the same bow and says, okay, I think it's 63 grams. Then musician 3 says that it's 60 grams. And we can do this with a lot of musicians, and we will have all these responses. So in the method that we are going to use states, or is based on the fact that there exists interparticipant variability, which would average on the exact weight of the bow. But this is not the task that we are going to ask the participants to do. we're going to ask them to do a discrimination test, that is to detect differences between two stimuli. For example, if we have a bow that weighs 60 grams and a 63 gram, can they differentiate them or not? And we see that this variability, when we are talking about population of violinists, it can overlap. So there may be people that detects or perceives the red bow as much heavier, and then it perceives the green bow as much lighter, and finally says that the bow and the red bow is heavier than the green bow, even if this is not exactly the case. So this is just to picture what the foundations of signal detection theory, which is that decision making occurs amidst some level of uncertainty. And we have here the distributions that I was showing you before. And in this case, it's with two kinds of stimuli, in this case, auditive stimuli. So for example, if you have a signal that is just noise, and then another signal that is noise plus and a specific sinusoidal signal, when we ask them if these signals are different or not, depending on how they perceived in which point of this distribution they perceived the first and the second signal, they will say if they are different or not. And we can, and there is this measure d prime, which it will be the distance between those distributions, those stimuli, and represents the sensitivity of or discriminality of, in our case, of a population in a perceptual task. Okay, so sorry for the for this parenthesis, but what we did is apply this this theory for our perceptual experiments, our discrimination tests. So back to bows, we performed two perceptual tests. The first one, we asked them to hold and shake the bow in the air, so that they were not playing with it, but just evaluating the bows by holding them horizontally. And we used this this sequence, this type of test, which on which we put a reference bow, which was in all cases bow A, at the middle of the sequence, and we could have two variants. One with the bow A, then the reference bow presented as the reference bow in the middle, and then an anonymous bow, or sorry, anonymous, no, different, or the other way. And we asked them to answer this question: which one, the first or the third, is equal to the bow presented at the middle, which was always bow A. And on the other side, the second discrimination test that we did, it required to play with the bow. And for this specific test, after some tests with two musicians before inviting all the musicians, we decided that this design was better adapted for this specific task, because it presents the reference bow twice, always before an anonymous bow. And we asked them to solve this question also: which one is the second or the fourth equal to A? So let us imagine that there is something and someone that is very discriminant, that it's very sensitive to these changes in bow mass distributions. They will always give the good response, so they will have a 100% rate of answering the question correctly. But let's say that there is someone that doesn't perceive any of these changes at all. The rate of correct answers will be 50%, because you have one possibility out of two of responding correctly. So to inform further their responses, we asked them to give sureness level. How sure are you of your response? So that we can use this in the model for calculating the sensitivity of the population of participants. So in both tests, the retesting was not allowed, and we invited a total of 20 participants, 10 of which were professional violinists. So here it is D prime, as I was presenting before, and the results of both discrimination tests. So the first one which required to hold and shake the bow in the air. We see that the bows that have a variation in the moment of inertia, well, were mostly, I think it was 14 out of 20 who detected that who said that this was the different bow, but it's not a significant discrimination, meaning that the number of participants that answered correctly does not reflect, we cannot infer that the population is able to discriminate it better than chance. But for the case of bows with variation in the position of center of mass, we see that when they hold it horizontally, a little variation for bows A and D did not seem to, we cannot say that it was perceived, but we can say that the bow with a big variation in the moment in the center of mass position was significantly perceived as different. So that was for the first test. And for the second test, which involves playing with the bow, we have bows with different moment of inertia, meaning bows B and C, that have that were significantly discriminated from the reference bow A. And that was, we cannot say that bows D and E were significantly discriminated from this study. Okay, so we see that at least when playing, a moment of inertia seems to be an interesting parameter to have a look when we are adjusting the bow mass distribution. And then, since we wanted to check what they perceive as different, we performed this free evaluation test on which we asked them to give their opinion on what had changed when we move from bow A to bow C or from bow A to bow E. So the task in this test was to play with the reference bow and then with a bow, either bow C or bow E. And by already knowing that it is different, we are not longer asking them if they find a different. They know that it is a different, the bow has changed somehow. To describe what has changed. And from this free evaluation test, for the case of the bow with a high variation of the moment of inertia, we see that the comments they evoked were distributed in this, well, we analyzed all the comments that they verbalized, and we categorized them by 4 principal categories, which were S for spiccato or bouncing related behavior of the bow, H for heaviness, P for playability or comfort, and O for other. So we see that if we compare their comments when we change the moment of inertia and when we change the center of mass position, that is the diagram on top and at the bottom respectively, the proportion of comments relating to a change in spiccato behavior or a bouncing strokes behavior is larger when we change the moment of inertia. And on top of that, I don't remember if there were 4 or 6. I think there were 6. No, I think there were 4. Well, they commented the displacement of the bouncing point of the bow. We did not ask them to check where the bouncing point of the bow was, but they freely commented that they felt they feel that there is a change in this specific playing parameter, we would say, of the bow. And then on top of that, we decided to analyze the comments of the heaviness category, which was more or less on the same proportion on both the change of moment of inertia and on the center of mass position. And we see that there is a change in the perception and perceived heaviness when we change both parameters, meaning that for case of the moment of inertia, when we increase the moment of inertia, there's a perception that the heaviness of the bow has increased in general. Four of them were talking about an increase on the tip. Here I colored it as if it was true or false, meaning that we had 3 spots where we were changing the mass of the bow, and there was an increase in the moment of in the weight of the frog, and an increase in the weight of the tip when we move from bow A to bow C. But in general, they commented on an increase of the perceived heaviness. And similarly, but on the other way, for a displacement of the center of mass towards the frog, which was the case of bow E, people perceived it as a lighter bow. So as a conclusion of this first study, we see that violinists did not seem to perceive variations in center of mass, at least not as much as the one of as a variation on the moment of inertia when playing. But when they were holding the bow, they did perceive the big variation in the center of mass position, and they perceived it as a lighter bow. So we see that variation in this center mass in the bow mass distribution alters the perceived heaviness, and we see that people is able to detect even slight changes in the moment of inertia of the bow when playing. And since they were commenting significantly change in the behavior of the bow that had a different moment of inertia when they were performing bouncing strokes, we decided to do another test on the influence of this parameter, the moment of inertia, on the bowing parameters of bouncing strokes. So we will focus now on the performance and less in the perception, but it's people playing, so perception is always in the equation. So what can we read about sautillé and about the bouncing point? Because there is something that marked me. It was that people perceived a change in this bouncing point of the bow when the moment of inertia increased. So Capet, at the beginning of the last century, wrote a magnificent book that I recommend to all of you on the technique of bow playing. And he divided the bow in these different parts, and established somehow the parts of the bow on which one should do this kind of bouncing stroke depending on the speed. So he already said that the position of the bouncing point depends on the speed of the stroke, but not only on the speed. Galamian later said that the choice of place of this bouncing point to perform sautillé, which is about a bouncing stroke, will differ with different bows. He talked about the elasticity of the bow, but here we are focusing on the moment of inertia, so we want to see if if we can detect these changes in when we change the moment of inertia on this particular bowing parameter. So we see that in the previous test, we saw that some violinists perceived a shift towards the tip, when we increase the moment of inertia. And we have the following question: if we fix the rhythm, because we already saw what Capet told at the beginning of the past century, can we measure this displacement when we change the moment of inertia? And are there other effects that are not only on the bouncing point, but maybe other bowing parameters that could be affected by this change? So to measure this, we used motion capture technology. So here in our laboratory, we have a room that is able to measure very precisely the position of these markers, and it is a technology that is used in other industries, for example, for video games, for reproducing the movement of the body in biomechanics. It's a very precise technology. So we put these reflective markers on the violin and on the bow in order to track their position and infer what we call the bowing parameters. It's not me who called it that. There's Schonderwald and Demoucron at the past who already worked on that, and beforehand it was Askenfeld. So it's the bowing parameters. What we call bowing parameters are the degrees of freedom of the bow related to violin playing. Okay, so degrees of freedom, I mean in the position. With knowing these 6 parameters, we can position the bow and its orientation in the space at every moment. So there are 3 distances, which is the distance from the bowing point to the prog, here represented in black. The distance between the bowing point and the bridge, and also the distance between the hair and the string, which in normal bowing situation is close to 0, but when we are using bouncing strokes, we have positive distance between the hair and the string. And then we have 3 angles, which is a tilt in charge of which controls the amount of hair that we are putting on the string, then the inclination for choosing the string we want to play, and the skewness. This is a measure of the perpendicularity on which we are bowing our instrument. So we performed 2 tests of these bouncing parameters, of these bouncing strokes, with 16 violinists, different from, I think there were 2 that already did the previous test, but there were a mostly different sample of participants from the previous one. And we performed 2 kinds of tests. First, what I called a technical test, which consisted in finding the sautillé point of the bow on different strings and different dynamics, and once they have found them, to keep it for at least 5 seconds so that we can calculate the average bowing parameters afterwards. So we did this test with 2 bows with contrasting moments of inertia in 2 dynamics, piano and forte, and on 2 open strings, G and A, and at a fixed rhythm with a metronome that we installed that we used in this motion capture room. So now I will show you how the data was collected and how this virtual room, how our software detects the position of both the bow here at the left and the violin at the right. Maybe you are able to hear something, and we did a sound check before, so maybe it's not very loud, but it's not really important. So this is how the test. So this is the room with all the cameras, and the test consisted on putting the bow at a specific location, which we predefined with all of the violinists, and was the same for all violinists, and to start moving the bow at the given rhythm until finding the bouncing point. And once they found it, they had to keep it for at least 5 seconds so that we could average the bowing parameters afterwards. And then we decided to, since this was quite an aseptic and test, we decided to do some music, and we asked them to play the overture to Mozart's Magic Flute, which has multiple quavers in bouncing strokes, specifically in spiccato. So this task, we asked them to perform this excerpt with the two bows of contrasting moment of inertia and on two dynamics. We did not ask them to do this in two dynamics, but as I will show you, we selected two different bars that had the same quavers in spiccato performed with different dynamics. And we fixed the rhythm also with a metronome. So this is the excerpt that most violin players may know, because it's widely asked in orchestral auditions. And maybe you're able to hear how the first line of this music sounds as performed by one of our participants. So as you can see, it's quite bouncy, and as I advanced before, there are two bars that are identical, not in musical terms, but in terms of what are the notes that are in the bars. And they should be performed with contrasting dynamics, meaning that the first one, the quavers of the E flat quavers should be performed in piano, and in the second case, down here in forte. So we have the chance of having, in a musical context, two bars with identical bars with the quavers played in piano and in forte. So with all this data, we've had we could calculate the average bowing parameters. Here I am referring to the first test, so the one that consisted in looking for the spiccato, the sautillé, the bouncing point of the bow. And each color in these graphs represent a different musician. What I am representing here is two bowing parameters. I selected two of the six bowing parameters that we can represent. And in this case is the distance from the bridge to the bowing point and the distance from the frog to the bowing point. So we see that there are some musicians that consistently play, for example, here represented in pink, closer to the frog and closer to the bridge, that others that consistently play, for example, this one in legged ring, further from this from both the bow, the frog, and the bridge. We calculated this average, and we did the same in the case of the musical test. So here, this time in spiccato, we also calculated all the six bowing parameters, and since we have this amount of data, we are able to perform some statistical analysis of these bowing parameters. And we performed what is called linear mixed models, which are basically linear models, linear regressions, but that take into account the individuality of each musician as a random effect. This is widely used nowadays in data, big data, and this kind of research, in order to see if the effect of the element that we are changing from one test to the next test is significant or not. So we will have, for the technical test, three fixed effects, which are two bows that we are using, but also two dynamics, in this case piano and forte, and two strings, A string and G string. And for the musical test, we would not have a different string, because this E flat note is always performed on the A string. So we will have the two bows and two dynamics as fixed effects. And here I'm going to picture some of the results. and what they mean. So I am only showing you what we found, the specific bowing parameters for which we found that the bow, the moment of inertia of the bow, did have a significant effect on when we change it. So, for example, in the case of the distance from the frog to a bowing point, that is, if we play more towards the tip or more towards the frog, the moment of inertia seems to have an effect on this particular parameter. This is also called the bouncing point of the bow, whereas it's more towards the tip or to the frog. And what we saw is here in the left, I am plotting the difference between bow C, which has a higher moment of inertia, and bow A, which has a lower moment of inertia. And we see that for bow C, this bouncing point is more towards the tip, significantly for the technical test, but also for the musical test, although it's not significant. But not only in the bouncing test. Well, what we see also when we compare these variations on the bowing parameters due to the bow is when we compare with other effects, for example, the dynamics of the string, we see that it seems that the effect of dynamics in where we are doing our bouncing, where is the bouncing point of the bow, it has a bigger influence than the bow itself, the moment of inertia of the bow. And it's also the case for the string, with 2 centimeters lower when we play on the G string than when we play the A string. And in piano, simply the bouncing point is more towards the tip when we play in piano than when we play in forte. When here I'm plotting also the 2 other bowing parameters for which we found that there was a significant variation when we changed this moment of inertia of the bow, and it's the root mean squared speed of these angles. So for the record, this was the bowing parameter responsible for selecting on which string we are playing, so the inclination, and the skewness is the one for the perpendicularity when we bow these strings. And we say that even it's less evident, less influential than other effects, it seems to be significantly lower this root mean speed. I have to say that this root mean speed, since we are fixing the rhythm, it's equivalent to say that the amplitude of this movement is lower. It relates is directly proportional to the amplitude of the oscillation. So what this means, in a few words, in other words, is that when we increase the moment of inertia of our bow, it seems to displace the bouncing points toward the tip, and not only this bowing parameter is altered, but also the amplitude of transversal rotations, of transversal rotational oscillations, which are this inclination and skewness when we are performing this kind of stroke. So that's the end of it, more or less. Let me conclude briefly on what I just presented to you. So we performed this perceptual experiment and investigated the sensitivity of participants, of violin players, to small and big changes on this bow mass distribution using a bow that was designed and built by Duilio specifically for this project. And we see that in holding, we can say that people detect variations in the center of mass position, but we cannot assure that they're able to detect other variations, such as the variations in the moment of inertia. But when playing, on the other side, we are able to say that there is a significant discrimination of these variations. So violinist is able to detect they are sensitive to variation of this parameter, the moment of inertia. and they actually verbalizes it differently than the variations on the center of mass position. So this inspired the following experience that we performed with another set of musicians. And we saw that the moment of inertia actually has an influence on the bowing parameters by reducing the amplitude of these oscillations, on the skewness and the inclination, and also by moving the bouncing point slightly towards the tip. So is 1 centimeter perceptible enough so that so much people is able to detect it? I don't know. But that's the what I have also some perspectives, but there are more general perspectives of what could be made afterwards after this research, which will be to really explore the relationship between the perception of the violinists with other parameters that we did not get to measure, for example, the response of the string, and complement that with microphonic recordings to have a broader vision of how different bows may affect the perception of the violinists. And other mechanical properties are also very interesting, although much more difficult to investigate by keeping the other mechanical properties unchanged. I mean, changing the elasticity of the stick is not an easy task, and also to come check how the different bows may influence the muscular efforts of the musicians by measuring with electromyographical sensors or other. But this is for future research, and I thank you very much for your attention.
All right. Thank you very much, Victor, for this fascinating study. If you have questions, if you can use the raise hand function, which is in your React icon at the bottom of your screen. But if you can't figure out how to get it working, you can always send a message in the chat, which somebody already has already. But let me just first start with a clarification question on the playing tests. Did the players use their own violins, or did they use the same violin that was provided?
Yeah, you're talking about the playing test in the motion capture.
Yeah.
Yeah, they used the same violin. Sorry, I forgot to specify that. They used a violin that was built by George Stopani for the project, Bilbao project, and a big hi for him. And yeah, everybody used the same violin for this study,
Okay.
specific study, and all of
Right.
them used the same hair tension. Also, we measured the hair tension so that we imposed the same tension for all participants when we were measuring their bowing parameters. Sorry.
Okay, so let's start with the questions in the chat. Okay, Leo has two questions. One is, how can I easily measure the moment of inertia at home for my bows?
Yeah, well, I think that the easiest way will be as the one that I showed you here before. So I did this really with materials that for plotting this amplitude, this oscillation, I used a GoPro camera to detect it, the frequency more precisely. But I think that this approach will be a good, a fairly good way to measure or to estimate the moment of inertia, and it consists on hanging the bow from the thumb position. Here I did with a cloth spec, so I think it's some kind of material that anybody can find at home. And also here I am showing what you can see here in this axis, which will be the rotation axis. It's a simple metal rod that I used, and I made sure that the bow could oscillate freely around this position. And then for the calculation, you just have to measure the center of mass position from measured from this axis of rotation. It's represented here as xcm. Then the gravity at your location, but it's normally 9.8 unless you are in Mars, and the total mass of the bow. And then it's only the only thing that you should measure is the period. You can do it different times if you want to increase your accuracy. But just measure how much with a chronometer. How much time does it take for your bow to perform 10 oscillations? And then you take this time and you divide it by 10, and you will have the period of your oscillation. And you just have to put this period into the equation to obtain your estimated moment of inertia.
Okay, so all right. A related question was the moment of inertia measured with the bow loose or at plane tension? And Claudia said it should not matter as it doesn't change the weight.
Absolutely. It changed what it changed is the damping, because when you have your hair that is not under tension, there is more surface of the hairs that reduce the amplitude of the oscillation, but it does not affect significantly to the frequency of the movement. And we perform different tests, and the difference between the bow under tension or without tension is not very high. What can change, and this is maybe not that negligible, is that the position of the frog may change when you are increasing your tension. It's just a few millimeters, but it depends on the bow. It depends on the position when the bow is loose. So I would recommend to do it on a normal tension, playing tension, so that this doesn't have an effect when evaluating the moment of inertia of someone that is playing with it.
So, back to Leo's second question: what role would Young's modulus play?
In this case, oh, for the bouncing.
Well, he doesn't say in what context. I think, you know.
Okay, so the Young modulus is a measure for the elasticity of the wood, and it may play a role on the mode of vibration of the bow. It could have an influence on the vibrating frequency of the bow on the string, but I don't see now how this could relate for the differences in the perception. Because now here, sorry? Sorry?
Sorry, I just muted
The answer
somebody.
is that we don't know yet.
Oh,
I mean, you did the first study you didn't present in this talk, Victor, was with two bows with different Young modulus of the sticks. And your hypothesis was that could maybe change the transients, but we didn't notice anything. We didn't measure
because
anything.
here I am mostly talking about mass distribution. I'm not talking about the elasticity of the stick, because we are always using the same bow. So, but I know I know that the elasticity of the wood is an important parameter for selecting different woods for the bow. For construction bow. But if you have any idea, I am more than curious to.
yeah. Okay, Joseph? You're muted.
Thank you for doing this research. It's super interesting. A couple of questions. I wasn't clear about how the masses were attached. Was there something metal put into the bow at certain points, like a pin or something?
Exactly. There was a small metal plate who was glued to the head of the bow, and the other parts where we attached the let me, was here at about 15 centimeters from the frog. It was a metal clamp which was magnetized so that we could easily attach the magnets, and also in the screw of the bow was magnetized. So the three parts there were always the same positions. And,
Okay, so
yeah.
So those three positions stayed the same all the time.
Yeah.
And what was the piece of tape? Was that to cover how many magnets you had there?
Yeah, that's it.
Okay. Now I'm curious. Does one assume that you could imagine two bows with the same moments of inertia and balance point, but arrive by putting the weights in different places? Would players tell the difference? Do we know anything about that, or are there assumptions being made that it's the same thing?
So I think that you're wondering about higher moments of mass. Here I covered what we call, well, in mechanics, there are the moments of mass, which will be the total mass, the zero moment, then the center of mass position, the first moment of mass. Then the second moment of mass will be the moment of inertia. And there is no clear correlation on how higher moments of mass, for example, the mass times the distance squared, no, cubic
Cubed.
distance, yeah, cubed, how this will relate to mechanical behaviors in our three-dimensional, I don't know, but it's a wonderful question. But because I cannot
Okay.
imagine any movement more complex than rotations. I mean, center of mass, it has an influence on how the bow behaves aesthetically, and the moment of inertia is on the rotations of this element. But higher moments of mass, I had an interesting conversation with Duilio at the time, but I did not find any correlation with yeah.
So if you measured the moment of inertia but turned the bow 90 degrees, it would remain the same? It doesn't matter if the bow is rotated, that stays the same?
Yeah, it depends on where you are establishing your axis of rotation. So it won't be the same because if I am fixing my rotational axis, oh sorry, I don't know where. Let me check. Okay, here. If, for example, I have this mass distribution, I don't know if you can see and I am working on rotations that are in this way. If I rotate my bow and I do the same, I won't have the same distance from the particles of my system to the rotation axis. Here I won't have the same moment of inertia, in short, in other words.
Yeah, so Joseph, I think what you're getting at is you're not necessarily asking about the higher moments, but actually the three-dimensional, nature of the moments of the inertia and mass distribution. Because in Victor's simple model, he's not making certain assumptions of not taking into account, I believe, the three-dimensional distribution of the mass.
No, that's it.
Yeah, I'm really asking from a place of ignorance about bows and the research, but mean, if you place that mass at a certain point and put a different weight, it's going to change also the vibrational modes of the bow. Do we have a sense of, is that important, or it doesn't, it's not relevant to this because you're keeping that constant?
So if I can reach the same pair of mechanical properties, for example, the same mass, the same center of mass position, and the same moment of inertia, but placed differently, yes, this is possible, and we will have an effect on the modal mass that we are adding on the bow. Yeah. How does relate to the dynamical behavior of the bow? I have not investigated yet, but I think that it could have an effect indeed. Yeah.
Okay. Well, thank you. Keep going.
Thank you.
Van, can I jump in here?
Sure.
So as you change the mass distribution with your little masses,
Yeah.
you will change the modal frequencies in some degree.
Yeah.
So you can have statically the same moment of inertia and have the same total mass, but have different modal frequencies, Joe.
Right. So is that important? Or I guess it doesn't bother this experiment because we're not varying it in that way. Is that
Well, I'm just saying you've thrown out another variable, and yes, it will have a sensitivity. That study hasn't been done yet.
Yes.
okay? Thank you. Yeah, there's so many things to.
Yeah, my comment would be that this experiment assumes that any effects due to that is smaller than these other the effects of the center of mass and moment of inertia.
Yeah.
I would agree. I would agree. Where, people have played with looking at those vibrational modes. That goes back to some real early work on the bows. You can change those. You can change the stick frequencies by taper and mass distribution. So we need a bow maker.
I think we have at least one here. I think I saw Matt Whaling. Is this what bow makers do? Do they, do they add weight in, at the frog or at the tip consciously to shift that, or is it more to shift certain playability notions or their feel? Or Victor, are there conclusions from this experiment that can feed directly to a bow maker and they would know what to do?
I think that the most significant conclusion is the awareness about the moment of inertia, because as I was talking before with Fran, we were not sure that this is a significant parameter to which bow makers pay attention, but I am not a bow maker myself, so I will be pleased to ask if anybody. But from what I have read from these books on bow making, is that the center of mass is an important parameter, and bow maker seems to vary the density of the winding material to reach the desired center of mass position. But I did not find, maybe I have to look better, but look for it, but I did not find any concerns about the density of the moment of inertia itself. And
I think Joe Reagan, you cite him. He studied that, didn't he, Fan? Didn't he show us a setup for?
I don't know, but I think Victor mentioned Joe Reg. In my very limited data points of talking to bow makers, I do know that a very few bow makers are aware of this, but most bow makers are not aware of this. But that's not a scientific sampling. I mean, if Matt is willing to comment on this, I mean, I know he's on here. Be interested in his views on the subject matter.
And Duilio is here as well, so maybe Duilio could
Or Duilio,
comment
exactly.
on that. But before that, maybe Victor, you actually measured the modal frequencies. Don't you have the graph somewhere that you could show?
Yes, I was wondering if it was a good idea to show that, but I fear there will be much more questions. But yeah, we measured with these two bows, but the modal behavior of the bow under this constraint of string contact between the hair and the string. So basically, we held our bow at this position, what we call the pivot point from a hook, and we excited it as we would do with a violin plate or an instrument. And we measured this vibration here at the frog, because we found that it was a nice place for having at least the two first modes of vibration of the stick of the bow. And it was so this is how these modal frequencies are altered by the moment of inertia. It's very subtle, and it just of a few hertz, and we were not able to measure at positions at so here I will first explain what I am showing you here. The horizontal axis is the bowing point to frog distance, so the contact between the hair and the string, and more towards the right it will be more towards the tip. Okay, so we started our measurements around 30 centimeters from the frog, and at the top is the frequency of the modes that we detected from these measurements. So we will have the first and the second mode of both bows A and C. I remind that C has a higher moment of inertia. And we see indeed that for a moment of inertia of a higher moment of inertia, this vibration is slower. But again, yeah, that was what we discovered, and it's well explained by the theory, in particular from a model of Askenfeld that was reused by Goff at the time. And yeah, there is a variation, and I tried to explain the displacement of the bouncing point towards the tip. It could be explained by this shift on the frequency. For example, for the same, if we want to measure a mode at a frequency of 13 hertz, for bow A, it's closer to the frog than for bow C. We will have the same mode because these are modes that vary depending on the contact point of the string. And there is a shift depending on the moment of inertia towards the tip when we increase it. And I think it's a good clue, but I have to improve the model of the spiccato or sautillé model, and that's not an easy task to do because everyone jumps differently, I would say.
Okay, so let's continue with another question from the chat.
Yeah, sure.
The effects of gravity change depending on the angle that the bow is being played, much less when playing on the E string as opposed to the G string. Was this factored in the experiment?
Yeah, so that's why I totally agree for the hypothesis of the influence of the center of mass position on the perception of the weight of the bow. The effect, if we hold the bow vertically, we wouldn't mind if the center of mass is at the tip of the bow or at the frog of the bow. We will feel the same. I mean, if I hold the bow like this, the weight of the bow will fall directly onto this way, no matter of if the center of mass is at the tip of the bow or at the frog. And it is maximal when it is horizontal. So knowing that, if you can remind me the question, if that was taken into account, yes, we asked them to hold the bow horizontally. And when playing, we asked them to play on the G string, but we asked them to play freely mostly. So we wanted to see if in an ecological environment, because we did not want to put any constraints other than please play some bouncing strokes, but most of them did this naturally, and we did not ask them to play only on the G string for keeping the bow horizontal. So the answer will be no in the playing test, but yes in the holding test. I don't know if it's clear. I can reformulate it if needed. Let's see the chat.
Okay. Are you looking for something, Victor, or should I go on to the next question?
No, you can go. Yeah, go on.
Okay. So the next question is, you made measurements of the mass of the 14 modern bows, but are there measurements of the moments of inertia for a variety of historic bows?
I am looking for that dataset. If you have it, I will be more than pleased to have that dataset, but unfortunately, I was not able to access any significantly big, and historical bows. I think it's a very interesting population of bows because the morphology of the bows are not that strict, I would say. And we will find different, radically different moments of inertia from one to another.
Okay. Matt, do you want to have the floor? You're welcome to have the floor and speak, if you unmute yourself.
So Fan asked earlier, or one of you guys asked, do bow makers tend to use this information when they're making bows? And it seemed like the general consensus was, none of the bow makers I talked to do this. And I would say most bow makers at an upper level are thinking about this sort of thing. Just like a violin, the bow is this holistic thing. There's a whole bunch of parameters as you're finishing a bow, and particularly if you're someone who's working directly with clients, you're thinking about this is a very important parameter in the finishing of the bow to try and bring out the best vibrational modes of the bow.
Okay, so but specifically though, do bow makers pay attention to the moment of inertia?
No one is using that term, but most people are feeling a bow, and that is something that's sort of intuitively being factored in.
And how do you feel that? I mean, what type of things do you do?
For me personally, I'm playing the bow, feeling how the bouncing point's going to change. Although you can also change bounce point by how you're cambering a bow, doing overall weighting. I very much respect this research that's going on. One thing that is sort of not a real world principle is that you can't just. I know it's changing a number by putting a whole bunch of weight right here, but that's not the same as changing the whole weight distribution along the entire stick. And I'm sure you're aware of that. And I know this is, but so at the moment, I'm sorry, I can't put it into analytical terms, but I can tell you that people think about it.
Thank you very much. I have a question now that I have the opportunity. Do you change the tip plate a lot, or is something that because I have heard that a bow maker friend of mine that he had a violinist that came and told him that he wanted a silver top tip plate, and this is one of the elements that would increase significantly or decrease significantly this moment of inertia. So I was wondering if this is a parameter that you change a lot or is not that important, the tip plate.
I personally change it quite a bit. if I'm making a bow, I always start with a non-metal tip, simply because it's very easy to remove a tip like that. And I always in my mind is, if I change this to a metal tip, what's going to change in terms of sound, in terms of how it feels like it plays, in terms of bouncing stuff. I'm also, by the same token, I'm thinking about, do I want a adjuster button that's a 3-piece button, or a single button where the silver is going the entire length of the button, because that's going to change balance point and therefore massive inertia and other things. So I personally am thinking about that a lot. Not all my colleagues do.
Okay, thank you very much.
Joseph?
I wonder if, as we have Evan here, drumsticks, the same thing, the same sort of considerations must be at work. I mean, how heavy it is, where it balances. Do they research drumsticks, Evan?
I think it's kind of, there have been people who have written papers on drumsticks, and the impact on them, the design of the nib at the end, and all those sort of things. So balance points affect your rebound. I play with a different set of drumsticks. I have some that are very narrowly tapered, and those are quieter sticks. Different wood materials will give you also different impacts because they're of how hard they are. It's like changing the tip on your impact hammer. So there's a lot out there, but I think this is kind of like, many of the drumsticks were invented and developed, and the field was established before anybody was doing much research, right? And then as they got into some things, we can explain why these different designs probably evolved. And so I think it's very much like, violin making, where we set up an expectation and a preference, and then us as musicians learn how to use that tool, right? And so when somebody gives me something novelly different, I have to kind of adapt my techniques to pick up whatever that new stick may be able to give me.
And so all of us to say, are drummers, percussionists, as passionately sensitive about their sticks as violinists are, or is it a less sensitive?
I think all drummers will, and a large part of this is cymbals. So I have certain sounds I can get out of my cymbals with different types of sticks. On my drum heads, I'm less concerned. So it's really my interaction with my cymbals that can make my drumstick choices. And so, yes, I think there is a lot that we learn, and I think drummers become married to sticks they like and they know how to control. So I use maple and hickory. They're completely different sounds on my cymbals, and depending on what venue I'm playing in, I will use one or the other. And tip design will also change that. So yes, if you look at any drummer's bag, they will usually have a cadre of sticks that they know what to expect out of them. And you'll have brand loyalty and all that sort of stuff.
And when you say a different sound, you're not thinking that the materials of the stick affect the sound, but they affect the way you can use it?
Well, no, it's kind of like on an impact hammer, you have a hardness. Different woods have different hardnesses, right?
Okay,
so if I want more ping, I will use a different type of stick. And the tip size interacts like that, like your impact hammer. So it's tip shape, taper of the shank, weight of the stick. I used to be a drum tester many years ago. One of the drum magazines sat there and said, we want amateur testers. And I said, well, everybody who's reading this magazine is like 15 in their basement, and I was like 35. And I said, I'm part of I'm part of, you're going to make me one of your testers because I'm just unique. They sent a series of either marching band or heavy metal sticks. They're really fun to play. I can't use them in performance. They just have a nice bounce to them. They have a nice feel to them, but they are just too freaking loud for what I play. So there is a wide range of things you can do with drumsticks.
Well, thank you. Sorry, Victor, I didn't mean to distract the conversation.
Yeah, Joseph, I want to add that because of the variations in the wood, so it's not just the design of the drumsticks, but you get huge variations in the sticks for the same manufacturing process. And most drumstick manufacturers, and we're one of them, will do various, depending on the company, various types of sorting of the sticks for either for weight, for balance, for the tone, the basically,
Just drop it on a tabletop, and I have two identical sets of drumsticks that are short that I use kind of as an effect, but I can't mix that pair. They have to be one set or the other, not one from each, even though they are supposedly the same drumstick.
Okay. And well, actually, which makes me ask, Matt, do bow makers think of the notes of the bow, the modal frequencies? Do people tap their bows, drop them on tables, anything like that?
Yep. That's a method used by quite a few bow makers. I'd say certainly the majority. And if you have a musician who's ordering a bow and you're thinking about what is their violin, if they have something that's kind of a screecher violin, you're going to look for a piece of wood that's accentuating lower frequencies so that you can kind of take that away from that. And alternatively, if someone, sometimes someone will say, oh, my A strings really could use some brightening up there. And I'll be looking for wood that I know when it comes to the finished wood bow is going to be accentuating those frequencies.
That seems amazing to me. Has anyone researched this?
You can tell here I am sitting in my basement. I have no idea.
Oh no, well, that's why we're all here together. People with
Yep.
different backgrounds. Well, Claudia, have people, right away invites, do bows bring out different areas of the spectrum? That's a fascinating thought.
I mean, we know that people are talking about the sound of the bow, and it's not clear. It's not clear. We have now Amélie Picard, who she's been mentioned by Victor because she did an internship with us. She's now doing a PhD on the bow as well. So maybe in 3 years we'll have some clues about that.
Okay. Well, actually, let me run by the idea for experiment I was thinking to do at Oberlin if there's time. I might have mentioned it before. And let's say you have 5 violins, 10 bows, and a bunch of players, and you ask the players to find the best bow for each instrument. Would a preponderance of players, would there be a tendency to match instruments with bows, or would you think it would be randomly depend on the players? So is the sense of matching an instrument to a bow real, or is it really just matching a bow to a player?
I think there will be maybe also a match between the player and the bow. But if you're asking them to do this particular task, I don't know.
Because what Matt says, if that holds, it suggests to me that instruments that are overly bright, people will tend to choose bows that compensate for that. So there's the bow's talking to the instrument, at least in that sense. I'd be very curious to find that out. It'd be an interesting, easy test to do.
I don't think it's an easy test to do, Joe.
Why?
You've got so many variables in that. I mean, it's easy to gather the data. I don't know if it'd be easy to understand it, but give it to Matt. He knows what he's talking about.
Matt, what do you think?
In my experience, it's a triangle of bow, instrument, and player. And all 3 are putting variables into that. Joe, we have our colleague Scott Slider, who's incredible at, if you put 5 bows down and 5 instruments, and a player comes and plays for about 3 minutes, Scott will go, you want bow A with instrument C. He's incredible at it, and there's some, it has to happen through trial and error to most of us, but it's definitely a triangle where all 3 parts are contributing to the final sound.
So you're saying he can predict which,
He's really good at it. It's incredible to watch him do it. But
so
he's
in other
not,
words, he can pick a bow for an instrument and then the player come in and will pick the same bow?
no, he's just really good at, he'll play a bunch of instruments, he'll play a bunch of bows, you know, we'll be at Players Meet Makers, and he'll just sort of know, you know, he'll watch the person play and understand their technique really well. And then he'll just sort of say, I think you want this bow, and I think you want with this instrument. He's really good at it. But
And
that's
the-
more,
And
that's
then the
more
player
just,
agrees with that though.
you can hear it, you know, instantaneously, 4 out of 5 times.
Oh, wow.
I want that man in my,
Can you hear?
my
Sorry, what can
woodshop.
you hear?
What can I hear?
Yeah, you said you can hear it instantaneously. What can you hear?
You just hear way better tone production. You know, it's just how sometimes someone's playing a violin, you kind of cock your head and say, wow, that's really nice. And sometimes when someone's found that match of themselves, the instrument and the bow, you don't have to think about it. It's just like, there it is.
And Matt, is there a particular part of bow making you would like to see research in? I mean, are there some questions that you have or your colleagues have that you think might be answered by research? Most of what we do, of course, has very little to do either with violins or bows to the actual process, but it's good to know what thoughtful makers like you are interested in.
You know, I'd have to think about that a little bit. I mean, there's so many things, just like it's great that research is sort of starting into the bow world. I think the violin, you know, had the real in-depth research started many years ago, and it's now getting around to the bow. And I think it will really pay off in a number of years. So for the moment, I don't really have any. Thank you for asking, but I can't think of anything off the top of my head. So I did really like the question earlier of some modern bows were tested for moment of inertia. How does that compare to historical bows? That'd be a great thing to find out. But there are some bows that it just seems everyone knows they're the fantastic bow. But I think many more bows are fitting into what is the right bow for that player and their instrument. And that's going to vary. There isn't, like, just like a violin, there's not the magic formula.
And do you think there's a general difference between modern bows and historic bows?
In terms of what?
Playing qualities. Could people distinguish them in blind tests? I mean, the sort of things we did with violin, we were always disappointed by the myths. No one's actually done it with bows, though.
I don't know. It'd be a great experiment to find out. One of the things that's really difficult is, and I certainly understand, I have a background, I have a degree in chemistry, so I certainly understand scientific methods and things like that. If you look at the overall sound quality that people are shooting for, if you're doing a blind test of instruments like you guys did, which was fantastic, it would mean more to me, even though this throws in a whole bunch of unscientific variables. What if you took those instruments and found the bow that makes that instrument sound the greatest that it can with that instrumentalist? And how if you've got the perfect match on a modern instrument, how's that going to compare to the perfect match on an older instrument?
That's interesting. So you're saying find matches that really work and then transfer it across classes of instruments. That's a pretty complicated.
Yeah.
Because a lot of the other tests we've done on the violins is we've taken the player's bow and saying the player and the bow are one system. And Matt's saying that's probably an oversimplification of the problem.
It is.
Almost certainly, almost everything we do, we have to way oversimplify, and
Right.
that's the trick. What can we still learn?
I have a question for Joseph, because you proposed an investigation of different historical bows, but modern historical bows or Baroque historical bows. I mean, to keep
Well,
the same morphology of the bow, or?
No, I was thinking more in terms of, as in old Italian violins versus modern, mostly copies of them. So I wasn't thinking of earlier bows. Fan and I remember we did a very preliminary blind test with bows in Chicago.
Yeah, we had, but
Carbon
that was
fiber bows and-
concentrated on whether people can detect that, whether it was a composite, you know.
We didn't ask them that, but we just threw them in.
Right,
and
right. We
analytically singled them
didn't
out.
tell them that that was part of the experiment, but we had a bunch of carbon fiber and composite bows in there.
Yeah.
Um,
Well, Matt, do you think players could tell between wood and composite in a blind playing test?
Well, my business is making new wood bows, so I would say yes.
Okay.
But I mean, and it's also, the classification of wood bow versus composite bow, it's such a huge classification, and there's so many variables there. You in general don't have the top bow makers working in non-wood bows. And so you'd have to either decide, well, we're going to look for a bow maker who's maybe not at the absolute top of level of making, to look at his work with some of these carbon fiber bows. There's so many variables, and there's apples and oranges.
Yeah. So I wonder if you just put out a bunch of, well, it's so hard to say. In the test, Fan and I did, the overall favored bow was a rather inexpensive one, and there were some very expensive bows in there. It was a wood bow. So it's hard to, when you say things like top makers, it's hard to know. Not that, of course, I very much respect top craftsmen and understand what they're doing, but in scientific terms, it's hard to know what to do. But let's say we had a group of expensive conventional bows and expensive composite bows, and we had group of players play them and sort them, and then did one of Claudia's, what do you call it, free
Free categorization?
Yeah, free categorization. Do you think that they would appear at a category that encompassed the composite bows? That's what I wonder about.
No, I don't think so. Because we did some blind tests in Oberlin as well. With John, remember? And there was a Coda bow in composite, and nobody spotted. It was actually very liked, and people were so shocked to discover that it was a composite bow.
And there are fantastic composite bows. I mean,
it was the cheapest.
Really expensive composite bows nowadays, and that they are in the same range of prices of modern Pernambuco bows, I would say.
But are they? It's a hopeless question.
But I mean, it's the same for the hair.
Predictor of anything.
Now you have the synthetic hair, okay? Yes. And they are made often in very bright colors. So of course you can see it, and then you can see it, you can hear it. Everybody was agreeing, yes, we can hear it. We did the blind test and people couldn't believe it. They couldn't tell.
Well, and Joe and Fan, remember way back in Oberlin, we had that blind test where it was, ABX. And we've been playing around with violins for a couple of days, and then we had a bow guy come in, and he was like, any fool will be able to tell which bow is being played. And we came up with the same type of thing, as nobody could really tell, from listening, which one of the bows was being used. And he was very upset with us, thought that I was cheating him out behind the screen by not changing the bow, because he couldn't hear a difference. And he was the one who came in and said, any fool will be able to tell. So I think it gets back to Matt and his master matcher. I believe there is probably a match between the player, the instrument, and I think all of us select instruments that we can control. So I think there is that three-way dynamic. I think your simple test, though, of taking a handful of bows and a handful of violins, in Detroit this year or something like that, and just seeing if there's any consistency would be a great start.
Oh, okay. And I was saying it's simple in that it's easy thing to lay out. What do you think the complications would be?
Well, I think it's easy to gather the data.
Mm-hmm.
My guess is it'll be statistically difficult to make any type of correlation unless we get the magical thing that everybody goes, violin 16 and bow C are the perfect match.
That
You
will
know.
never happen.
No, oh, come on, don't say never.
Well, okay. Well, if we, I ask it, I don't have any intuition about that. I haven't spent a lot of time playing a lot of bows with instruments, but I've heard enough people say kind of rules of thumb about bows matching instruments that I would, like to see if there's some tendency that way. And you say it'll never happen because from trying it, or just from.
No, I mean, I'm just saying this because we have never seen any consensus. So I would be very surprised that suddenly we see a consensus. But
Okay, you haven't seen a consensus about which bow matches which instruments?
well, no, in general about musical instruments, which one you prefer, which one you like, which one is a good quality, which one is a low quality. I mean, any question we ask, we barely see any consensus, I think the only time I really saw a consensus is when people were not allowed to play the instrument. So they just look at two instruments, one yellow, one red. And this is the only time I saw a consensus. The red violin had a dark tone and the yellow violin had a bright tone. That's the only time I saw the consensus.
Okay, well, consensus is a high standard, but just a significant difference. I mean, in Paris and New York, we found significant differences, and we haven't found many since, or I haven't been following too much of what you do, but I understand that it's been, certainly from our last things in Oberlin, it's been very difficult to get anything that good. So I wouldn't be surprised if that carried through to testing bows, but nor would I be surprised if they did sort themselves out in some measure. Do you think there's bows that any player will pick up and think are bad bows? I mean,
I think it depends on the player highly, but not only on the player by its preferences or whatever. It depends also on I hypothesize on the position and experience of the player, what repertoire is used to do. And if you have a player that he's used to play some Baroque music where he's mostly accompanying other, and people talk about first range. I had comment c'est pupitre in English, Claudia? Sorry.
The music stand.
Okay, so in orchestra, I interviewed an orchestra violinist and talked me about this concept of first music stand bows and other music stands bows, because the role of the soloist, and I hypothesize that they are bows that support a higher tension to produce a louder tone, and back stand bows will be more comfortable tones in order to play, And there are also people that talk about soloist bows, but I don't know in which terms they are different, because I did not, unfortunately, have access to this kind of bows.
Well, I suppose what you're saying, I absolutely agree with. I like the idea, as we did in Paris, of defining the choice, like this is one I want to take home and try, or this is one I might use for the next tour. Just thinking about the Mozart example you use would be if you're auditioning for an orchestra, because you hear again and again the same excerpts that players have to play. They know them backwards. So maybe using those and say, these 5 excerpts, choose the bows based on those, with a supposition you have to play them for a audition. At least that might narrow or focus people in certain directions.
Yeah, and that's why we choose. Well, I chose this excerpt because it's something that everyone is in the violin learning, or when violinists are doing auditions, they know what the jury is expecting when playing this kind of excerpts. So it's when they take classes to improve their performance on these excerpts, they are all under the same. I mean, in this kind of auditions, there is no place for creativity in some sense. So it's most probable that they will all play most similarly, and I thought that it was the best choice for this kind of test.
And also, I mean, they are very challenging, each in a different way. And one of the things I think that makes it so hard with some of the blind tests we do is we're picking something like the opening of the Tchaikovsky, which everyone agrees is a great way of getting a quick sense of the violin. It's not challenging in any, it's middle volume, it's lyrical, it's nothing difficult. So we're not pushing anybody unless you tell them play it as loudly as possible or as quietly as possible. Where I think the genius of the excerpts as they've evolved is that they're really hard in themselves in particular ways.
So Joe, that suggests on your test, select two pieces, one that's really easy to play, you know, that everybody knows, and try and do the match, and then take one of your challenging pieces and have them do the same type of thing. Right. So now you've got, you know, the 3-way or 4-way split. I don't know how many variables I got in here right now. It'd be like, for this piece of music on this violin with this bow, this is my favorite bow, right? And for the next piece, I would use either the same bow or a different bow. Would be an interesting.
Yeah, that's very good.
And this is something that, for example, the concertmaster of the Berlin Philharmoniker once posted on Facebook that he has different bows for different contexts. And most soloists on their case, they have different bows for depending on which piece they are, because they find that this bow inspires me most for playing Bartok, for example, or it's not an inspiration, but a mechanical, something that will be measurable, maybe a higher moment of inertia that is better for bouncing strokes. Yeah,
I wonder if you came out for an orchestral edition with 5 different bows, would they let you change for the different excerpts?
Matt, have you got any comments on this?
I don't know.
I don't really have comments on what Joe just said. I'd like to go back to something that Victor said a few minutes ago about how people who are in first chair, soloists and whatnot, tend to want a bow that's going to have tighter hair tension and projecting more. In my experience, people who are doing more soloistic stuff already have the technique that they're projecting fantastically, and they're more interested in a bow that's going to allow them to do a lot of coloring and changing of colors. And through that, that kind of goes, if someone's at that level, they don't necessarily need to have a different bow for different sections of the piece.
I didn't realize that people, is it normally accepted that a tighter bow will give more projection, or just that you can dig in more with it? What's the thinking there?
I was more responding to just, that's sort of how, and I know Victor was probably just, you know, giving a quick synopsis to go in with the discussion, but tighter is perhaps not the correct, well, that was the word used, I think. So
yeah.
A higher tension, more sound.
Yeah.
I don't know. So what?
Well, higher tension. Yeah. Sorry. Yeah.
And yeah, my understanding from a lot of fantastic players use relatively, they don't tighten it very much. They use relatively soft bows and somehow make it work. Do you think
I agree. I agree.
And why do you think they do that? What are they gaining from that versus
I think there's an evolution of people's understanding of bowing as they get older. And most of the soloist people that we're talking about are a little bit older, not all. And you know, people grow up dreaming of their dream instrument, and they get it, and they sort of match their dream instrument to their crap bow. And then they have to go find a good bow, and they say, I want it to be just like this crappy bow I learned on. But what happens is that people get educated about instruments, and they learn more and more and get super into it, and then they get their instrument. Then they have to be educated about how the bow is very similar and has its own, it's very similar in that it has a lot of very small little distinct things that build up what a great bow is. And that's a learning process, just like it is with learning what a great instrument is.
Yeah.
And
Yeah.
That reminds me of a participant that she is a very an excellent violinist, and she only changed her bow that he had since she was like 18 or 19 years old when she turned 50. So she played with wonderful instruments that were lent by foundations and this kind of wonderful Italian instruments, and she only focused on the bow when she was 50 years old or older. So it shocked me at the beginning, to be honest.
Leo?
Yes, Han, thank you. I'm going to put in the amateur violinist perspective here. I'm an accomplished amateur violinist. I play in a string quartet. And when I was looking for instruments, I had a lot of international travel, and I played over 200 violins at shops around the world to decide what instrument I wanted to spend my money on. And that included everything from Strads and Del Jesus, which were, beyond my pocketbook, but nonetheless, I got to play them. And I developed this ability to have sensory perception. Well, the same thing evolved with my bow tasting. It's like wine tasting. And I definitely felt that as I played different bows and understanding that the bow is in fact harmonically coupled to the strings. So the bow can enhance various frequencies. And I found that different bows definitely affected the projection of the instrument from brightness to dullness. I made no acoustic measurements. And of course, my own bowing arm is going to affect that. But I felt as a player, I could clearly tell that different bows affected the sound of my instrument. Personally, I've always liked lighter bows. I have a Francois Lupeau, the second bow, an early 1800s bow. It's quite light, but strong Pernambuco. And I've found that this type of bow matched my playing, but matched the sound of my instrument very well. So as an amateur, listening to all of this, I absolutely agree that as a player, we should be attuned to how bows affect the sound of our instrument, not just how we feel in our arms. Anyways, that's my 2 cents for all of this as a player. And I'm loving these discussions as a scientist. The more I can understand about the acoustics and the equipment that I use, the more I can enjoy the tools, if you will. All right, thank you. That was my 2 cents.
Let me just point one sentence you said. The bow is in fact harmonically coupled to the string. What did you mean by that?
So if we think about the string vibration, primarily in the horizontal plane across the fingerboard, I mean, it does have this rotational bit, but the hairs are in fact in contact with the string. So there is some damping that the hairs make on the string as opposed to just, hitting the bridge with a hammer, an acoustic hammer, and seeing how the instrument responds. The hairs are serving as not only activating the string, but also damping the string. And those damping frequencies through the string are connected to the tip and the frog, and therefore through the wood of the bow. So the wood of the bow itself, whatever its mass and dynamics are, whatever the frequency spectra from the bow, are in fact harmonically coupled in some way. I don't know how strongly they are, but I feel as a player acoustically, I can notice that this bow really gives a brighter sound. It emphasizes brightness, or this bow emphasizes lower frequencies. Yeah, so I feel I can notice that from a perception standpoint. But that's what I meant about being harmonically coupled, is the string is in contact with the hairs, which are in contact with the tip and the frog, and therefore the wood. So the bow does have some damping effect on, the strings. That
reminds me of some because it is indeed, and in fact the hair is more spends more time in contact with the string than when the string slips under the hair during this slip and stick bowing mechanism. And there were some paper, now I don't remember now, that tried to match to couple the longitudinal frequencies of the hair
to the vibrating string, but I think that they did not prove anything. But I think that the quality of the hair and the quantity of the rosin that is applied and the tension of the hair is it's really important. In terms of the quality of the wood and the vibration frequencies of the wood, I don't have an answer for that.
Well, if you take, let's say you put a violin down on the table, you take a bow at tension, rest it on the violin, holding one end. Now tap the stick of the bow. Do you think you're going to hear that out of the violin?
You're asking me?
Yeah. I mean, I've tried it, but what was one thing, if they're directly coupled, then if you're setting the bow into vibration, you would expect it to radiate through the violin. Just as if you tap the bridge, it certainly does. You tap almost
You're tapping vertically, I assume, the bow.
And that, well, I'm trying to excite the the modes of the bow. I mean, and that's how they are. So if what I think is it's quite decoupled from the instrument, which suggests that there isn't an easy connection between the harmonics, the modal properties of the bow with the violin, because the hair decouples it so well.
Yeah,
I don't know.
So
It's
Joseph, that's a question I've always pondered, which is that assuming that there are differences in the sound, is the effect mainly the interaction of the bow with the instrument or the interaction of the bow with the player? And in other words, if the player actually bowed identically with the two bows, would it sound different? I tend to lean towards the camp that if there are any differences, it's mainly that's not it. The bow is not vibrating differently with respect to the instrument. What it's affecting is that the player is now playing the bow differently, and therefore the instrument differently. But that's just my opinion.
Well, no, that's exactly what the conclusion was from John's with Boeing machine. Is it John who is the retired engineer who brought that Boeing machine to Oberlin? And he found exactly that to be the case. If you put any bow at the same velocity and position, etc., it gives exactly the same sound out of the violin, which says
Yes.
that the wood has nothing to do with it.
There
Now,
were-
unfortunately, he didn't publish that.
There
so
was
we
like
can't-
one outlier of a bow that was quite a bit different. That was significantly different, but the overwhelming majority of the bows in his experiments when he used the Boeing machine, in terms of the spectrum of the output, it was basically the same.
And so the conclusion I got was we can all agree that it affects the sound of an instrument when someone's playing it, but is that the dynamics of the bow force players to do different things in order to get what they want. And that's a very different loop to investigate.
Right. Yeah.
And I wish someone would some more. Wasn't there some talk of reproducing that experiment, Fan? Were you with someone at your company building a Boeing machine, or Claudia, do you have a Boeing machine that could test that?
There is a Boeing machine, in Austria, and in a research group there, and they've published some papers with their robotic arm Boeing machine. So I'm hopeful that more data will come out of that research as well. But okay, we have somebody who's raised their hands. Nathaniel, go ahead.
Hi, sorry, I joined a bit late, so I'm not sure if this has been covered or not. Mostly what I am is a performer, but also a teacher. I also work on bows and do restorations. And I've been thinking about a few things that people have brought up here. I'm not sure if you've talked yet about the stiffness of the bow. Very stiff sticks and very flexible sticks as a player. When you get them in your hand, if you're sensitive to them, you are going to treat them differently. So the question about volume and how you're making volume, when I have a stiff stick in my hand, the instinct is to use pressure to make the sound. if I have a flexible stick in my hand, if you try to use pressure, you're going to bottom out right away. It's not going to work. So the way that you create your volume, the differences in volume, is you tend to go to the bridge more, use your contact points more variably, and use bow speed much more in the French school of using a lot of bow speed to make your sound come out. So it's a kind of a instinctual thing when you have a bow and you feel it. You say, "Oh, I know what this bow wants to do and how it wants to react." A very stiff stick is going to be totally different in your hand than something that's flexible. So the bow is telling you how to use it. And there was one other thing that just came up when you were talking about harmonic damping. I had quite a bright viola years ago, and I tried all these different sticks to see how it could make the best match with the viola. And eventually what I settled on was a Dodd bow, quite an old bow that had very dense wood, and it had the effect of damping the very bright overtones from the A string, but also bringing out the lows from the C string. So it in my hand, it felt like it was making that instrument much more bassy while keeping it from screaming on the high levels. And I don't know how to measure the density of that wood. It looked like very old, very dark wood. So that's also a factor, I think.
Could it have been doing that by forcing you to play a little further from the bridge?
With that bow, it actually made me bow closer to the bridge. Yeah, it made me want to bow slower. The density of the wood made me want to have a really slow bow speed and get closer to the bridge to get those bridge feet, tap dancing on the top.
So that's very interesting. Well, Claudia, has anyone given players a bow and a violin, or different bows and a violin, and say, play it and bring more highs out, play it and bring more lows out? Can they do it? Can you see that in the spectrum, the long-term average?
Done it.
I
think we haven't done much of recordings. We should do more of this.
Yeah, well, Luke and we were doing some tests, well, for something else, but we had a violinist that came in, a client came in, and so we got him to play the Tchaikovsky, and because we had a version of Ilya Kahler playing it, say, can you play it like this? And so he was great, because when he was playing it, he did a very different phrasing and everything else, which made it harder to compare with the convolved example. So he quickly picked it up, but then he was a good violinist, and every time he did it, we just said, do it a few times. He tried different things, and you could hear it. And then when we looked at the spectrums afterwards, there's a clear difference in the spectral balances, which makes sense. I mean, if it's sounding different, and he wasn't doing that by dwelling on one note longer than another. He was staying pretty darn close to what Ilya had done. So it seems like we can tell things from played spectrum, but of course people have done that. I'm just curious if it's been applied to bows.
Yeah, I think that that's a big concern to have when performing this, when trying to get rid of the musician and hear the violin through the playing of a musician, is that the bowing parameters for a given piece, and if it's Tchaikovsky or any piece, they will define the spectrum of the content in harmonics of the note that is played. If you play closer to the bridge, you're going to have a much brighter tone than if you play further from the bridge. And since the musician has this is able to change his or her bowing parameters during the piece, he's able indeed to change the sound of the violin. Because the excitation at the bridge is not the same, and I think it's Maybe that's the reason why we listen to violinists and less to the violin when we hear in Villefavard some of these experiments. But it's a problem.
But Joseph, that means that, you know, that's what I am still puzzled is like, how do we take into account these possible shifts in some frequency ranges by the player when we are, you know, because in the acoustic measurements, you don't have the player. And so this shifts in some of the areas, and that could be different for different players and could be different for different styles of playing, as you said, because the players that you were mentioning, you know, was able to emphasize some areas, you know. How do you take that into account when you actually measure the spectrum of the instrument just with your rig, you know? And
Oh, I don't. I mean, it doesn't
Yeah.
measure. That's not something it's measuring. That would be, I mean, how do we connect them? Of course, is a big question. But I suspect the way to connect them is to have ever tightening constraints on the players in terms of what they have to do to push them to the extreme edge, so they can't just adjust it. I don't know whether did that make any sense what I just said.
Not sure what you mean.
Okay, so this is getting farther from bows, but if you get them to play the Tchaikovsky, people, am I right in saying that we have a very hard time matching anything to anything without using AI? AI seems to be able to do it, so there is something real happening. But if you ask them to play it as loudly as possible, or as slowly as possible, or as quietly as possible, would we then, something which is, you know, they're working to the limits, and you know, it's like with the you know, the Schelling diagram. Are you pushing them right to the edge, or are you letting them waffle around in the middle? I don't know. That's just a
Well, Joseph, in all of this, we have to constantly go back to what is the question we're trying to answer, because we know this is a, you know, high-dimensional, multi-dimensional, highly complex interaction of multiple, you know, complex systems. So you know, when we think about experiments or things we want to learn, what do we, you know, we have to try to simplify it down so to have a shot at trying to understand some of these variables. So it's always in the context of what particular question are you trying to answer?
well, I'm quite happy trying to answer simple questions about kind of the physics, acoustics, and the measurement and all those things. But people keep saying, well, what about what about perceptual tests? And I always flinch because it just is such a vast array of complications. And I'm also annoyed that it's so hard to get good answers there. So I was only just thinking out loud, well, is there anything we can change in our approach to get better answers?
If I can shed some light by reducing if you ask your violinist to play very close to the bridge and very with low bow velocity, you are effectively making him a bowing machine, in the sense that you're removing the component of his freedom to play, and you are constraining the bowing parameters to like if you were imposing a robot to play like that. And I think that what they are doing in Vienna, it's very interesting because it is a robot that is able to reproduce the movement of one musician, and you can change the bow and you can change the instrument that is being played. So effectively you have the movement of a musician that is being reproduced, exactly reproduced or more or less reproduced by a robot, and you're able to come change the instrument and then check what is changing behind, and what we can see from the measured acoustic response of the instrument to that excitation.
Wow. So
But for now, they are not there yet at all.
It's very
Because-
promising. That's what I.
Yeah, but they say that actually to study bows, maybe not, because first they are not allowed able for now to change the bow. Plus, it's very difficult for them to calibrate properly the distance between the bow and the string. And that's absolutely crucial.
Why is
So-
it difficult to calculate the distance between the bow and the string?
It's a millimeter precision as of
Yeah.
the position of the arm of the robot is in millimeter. So when you are at the tip, a slight millimeter variation of at the frog, it can multiplicate up to the tip to 1 centimeter, and it's
So
Yeah.
I understand
So,
they're having.
so that means, so
trouble
they are very
determining-
able, so the movement of the arm, you are not 1 millimeter. 1 millimeter is not important for what you're doing with your arm as a player. But for the distance, 1 millimeter, you are in contact or you are pressing down, so that's can be a huge effect. So to actually measure what we are talking about now, where the player will adapt slightly by putting a bit more force, or, with a different bow, you have to play with more force. This will be completely beyond what can be studied.
Well, why can't they
with
just
such a
measure that while they're training the robot? I mean, you can measure in real time where the bow is.
yeah, but
No, but the problem is a precision.
It's
1 millimeter
controlling it.
precision. Sorry?
yeah, they don't have a force. They don't impose the force that the arm is doing during the bow stroke. They are just measuring the position of the arm
Yeah, let's see.
during the stroke. Yeah,
I would
I
have.
don't know if they are measuring also the position of the bow. I don't remember right now if they had but I don't think so. It's the robot. The robot it stops at the frog, so
Yeah.
it's a robot moving a bow.
Well,
I
I
can
was.
show you if you want to see that. Let me
You
check.
have the robot there. Can we bring it to Oberlin?
No.
Well, I mean, to study different things could be helpful, but for bow and to actually look at subtle effects, it's not possible. So, for example, like the latest study where they were looking at transients with different strings, the same bow on different strings, that didn't use a robot. It's not precise enough. They used a bowing. They used a monochord and a bowing machine.
So that's what we are talking about. If you see my
Wow.
screen.
And that's a robot they built there for the purpose?
I think they purchased it. Is quite a cheap robot.
It's a commercial robot.
Yeah.
But I mean,
Right.
I'm familiar a
Can we
little
get-
bit with this stuff. Without
Can we-
getting into the specifics, as Claudia and Victor has alluded to, certain things are doable with it, but it's a much more difficult problem than it seems on the surface to actually build a robot, a Boeing machine that can actually mimic humans. Because so one of the things is I think Claudia points out is that this robot can control position, and then even questions about to what precision and accuracy and repeatability you can control position. But the main thing is that it doesn't have any easy means of controlling force,
But
and that's critical for actual Boeing.
Exactly.
okay, so there is an interesting article in the New Yorker the past months about training robot hands, and they can actually using AI, and they can get them to tie shoelaces now. They can't transfer that to another shoe, and the way they're doing it is having a bunch of people do these things and the robot just reproducing their movements. But so I'm just imagining the missing thing there is the robot doesn't know what sound's coming out.
No.
If you put that in the loop and tell the robot to reproduce that sound, then you would start.
It's possible, yeah, but that's a different problem. It's what? Go back to
it's the human problem.
What question are you trying to answer? If the goal is to reproduce a specific sound, yeah, you can try that strategy that everybody uses now is machine learning and training itself like that. self-training.
Um,
Uh,
if we can say that there's a unique situation that'll give a particular sound. I mean, you have to have the bow in one place at one level of force, or you'll get a different sound. So if that's the case, then the feedback that goes to the robot should be the same feedback that goes to the player, which is largely through their ear.
Right, exactly. And you can probably program that. And then you might even discover that the robotic arm, you know, may not have enough control over certain parameters to reliably, consistently reproduce that sound, you know, because you can, you know, train, I don't know, you can train you know, a dolphin. Oh, you want to try to bow a violin, but if the dolphin doesn't have the, you know, the requisite appendages that's compatible, you know, with bowing, it's never going to work. So there may be fundamental limitations of this particular robot, you know.
Oh, I mean, if robots can do brain surgery, I mean, I think they can. It's just how much money do you want to throw
Yeah,
into
exactly.
developing
Right,
it,
right.
presumably. But I'm sorry,
Sorry.
Victor, were you saying something?
No, that you can continue. Sorry. Yeah.
So, I was brainstorming with Luca about this some time back, and it seems to me if you can, were we talking about this before? If you put a little video camera underneath the strings sticking out from the end of the fingerboard, and then it can see where the bow is, and let's say you put stripes on the bow every, you know, centimeter or something like that, it seems to me you should be able to tell the position and the speed. You wouldn't tell the force, though, but at least having the position and the speed would be a big help, wouldn't it?
Yes, and
A big help for what?
Okay, so let's say we give, let's say we can tell the bow position and the bow speed. We ask a player to do an excerpt 5 times, then we give them a different bow. Do they do the same thing? Questions like that.
That's what I showed you today. They don't do the same thing.
They don't? Oh, perfect. So we know that the bow is forcing them to do something else.
Yeah, and that opens another question, because I have now doubts. I don't know if it's the violinist who is acting differently on the bow, or it's the bow who has another playable zone, which makes the violin go to the most comfortable zone unconsciously. And this is a double. It will be, maybe it's something that is not perceptible for him. For example, moving your bouncing point 1 centimeter towards the tip. It may be, they may not be aware of that, because it's a really subtle change. But it's significant, but I don't know if it's perceptually significant.
Well,
I don't know if I am explaining myself well, but
I think so. And I agree with you that they are not doing it consciously. They couldn't possibly be doing it consciously. I remember trying to change the bowing point while I was playing. It was impossible. I mean, it'd be like trying to fall off a bike. You can't do it. I mean, you automatically compensate for things. So I think they're doing it, but it's part of an enormously complicated, you know.
well, the well-trained, the great players do it sort of unconsciously, but some of the players will know what's happening, because if they're aware of some of these effects of, you know, moving the contact point in a different, you know, with respect to the bridge and up and down of the bow, even though they're trained to do it, they have to do it automatically to be able to do it quickly in real time, but they may also be aware intellectually exactly what they're doing while they're doing it.
Maybe. Nathaniel, what do you think?
It is totally unconscious. And when you get a new bow and you're trying it, I've had this experience so many times. There might be a little place in the bow, like a centimeter, where there's a little jump, and you're drawing the bow, and all of a sudden the bow jumps. There's a little bobble. And if you play that bow for another even 15 seconds, you just, as a player, as a trained player, you somehow I don't know how it happens, but your brain maps that spot, you compensate for it, and the bauble goes away, and it's not, you've never even thought about it. It's just the first few strokes, the bow is talking to you, you're getting feedback from it, and then you just adjust how you're using it. So it's an amazing process, but I can't explain how it works.
Well, no, that's beautifully put, and I think it's exactly the problem we have giving different instruments to players. They immediately get a feel for it, and then they do what they normally do. Or it's like when you go into a different room, your ear sorts out the acoustics of the room very quickly, and then you adjust your voice or anything else accordingly. You know, if you're talking to your friend in a dead room and then you suddenly walk into this vastly echoic space, you just unconsciously adjust your voice to be better understood.
Right. Yeah.
Victor, did you record during the mock-up with the microphone?
No.
Because
With the
you
pickup,
didn't?
with the
Because I
pickup,
was thinking that we should look at the recordings and see whether we can tell them apart, you know. Can we hear which bow was used, you know? Can we tell them apart?
I don't in bouncing strokes. Oof, I don't know. Maybe
And for the Mozart?
in Mozart, maybe, but they are really different performers. Meaning that there were some students that did struggle to keep the tempo. So this is something also I obviously averaged out all the individual individualities. I don't know how to say, but they did, some professional, they did play really close, but they were different. But yeah, we can have a look to that too.
Because Joseph, when you say, you know, it's easy with the control parameters, you can just tell whether they play the same. I mean, we are working on this. It's not so easy to decide what is the same, when the thing is like, it's when you play, you actually play. It's not just one thing, you know. So you play, you adjust your control parameters along the note, you phrase with the next note. So what does it mean to play the same, you know? So can you align in time, because you never play exactly the same tempo, even if you have a beat, or you don't align and you look at how longer it is. And then if you align, what do you think is relevant? Do you average over the time for the control parameter? Or you actually look in the time, but then you have like series of vectors. What do you do with them to compare? You know, it's not defining that they play the same is very hard, actually.
Well, I'm never surprised to learn I'm wrong about these sort of things. But let's say we could get an easy readout for position and speed.
Yeah, because we have it, you know, we have
It's
it with the mockup. We have the easy readout. The problem is to actually compare things, you know. The readout you can have, with the mockup, we have no problem of getting the position, any control parameters we want, except for the force. We have it in real time.
I'm sorry, what is the mocha? Is that the
motion
capture?
The motion capture,
okay,
yeah.
okay.
So we have the position, we have the speed, we have everything as a function of time. But that means then we have signal as a function of time. And the problem is how to compare them.
I suppose what I imagine is if you have a line which is the length of the phrase and it goes down to indicate distance from the bridge, and you compare two of them, are they parallel? Or are they lie on top of each other?
The problem, they are not like this. They're more like this. And
well, of course, there's many variations, but let's just take a single note. You ask them to play a beautiful note at a certain tempo. I mean, and you'd ask them 5 times to do the same thing, and then they switch bows, and you ask them to do it again. Surely, I mean, if we can't tell anything from that, then I agree we're lost. But do we know that we can't tell anything?
No, that's not necessarily true, Joseph, because there's one thing I want to point out from experience, and which is that, and it's my opinion that just like with violins and bows, steady state notes like that, the overwhelming majority of differences between instruments and bows does not come from steady state signals like that. It comes from the startup characteristics of the note. That's where the differences are magnified.
I believe you. But do you think we wouldn't see any differences in the steady state? I mean, there are differences in the steady state, and
my own experience, and this is not controlled studies, but just just a couple of fooling around, is that what makes it difficult is most of the differences that we think we hear does not actually exist, but that doesn't mean there aren't differences. What makes it hard is trying to tease out the real differences that actually are there from our perceived differences. As an example of that, when I've done, bow comparisons, like somebody else is playing, okay, and they say, these bows sound different. Once I close my eyes and we do a bit more of a blind thing, guess what? A lot of the differences, if they exist, are much, much smaller if I can hear them at all. Same thing, this experience we had with testing bows back at Oberlin, over about a decade ago. I was convinced all these bows, I've got a whole pile of bows, I'm trying them out, sighted, and it's like, hey, these bows are all very different. Once I got blindfolded, I realized, all these bows are a whole lot more similar. It's hard to tell. I'm not sure I could tell them apart. But that doesn't mean there aren't differences, okay? It just means that the real differences are actually much, much smaller than we think they are. And you really have to run well-controlled experiments and blind experiments to tease out these differences. And that's very difficult to do. I mean, I have several bows, and I have absolutely no doubt those bows sound different, okay? But when I really close my eyes and I try them one after the other, I'm hard pressed to actually describe what the differences are, if there are any differences. Although playing every day, I just have a subjective reaction. This bow is very different. My bow A is very different than bow B. But under, blind conditions, when I just, do simple things like, steady state and stuff like that, I'm hard pressed to actually discern any differences.
Yeah, but Fan, I think there are two issues here. There is indeed the perceptual aspect, and what you're describing is perceptual differences, which are probably much smaller usually than what we believe.
Yeah,
and I will not disagree with you on this for sure. But for all the motion parameters, the control parameters, the question here is more how to actually analyze the data. And we are right now doing it. We have the set of data very controlled with one player playing a few times on different excerpts, 3 violins, okay, her violin and 2 other violins. So we have the data. And it has proven to be much more challenging than we thought to actually decide, is she playing the same on her violin than on other 2,
I'm not surprised. Yeah.
Okay, so
it's very tough, actually.
So
so we're working on it. So maybe in March I can talk about it. I don't know.
But just so just so I understand, unwrap the difficulty a little. So is the spectra, the long-term spectra, too similar to tell? Or I mean, there's
no. Here we are really working. We really want to see whether she actually plays the same in terms of gesture. We are not talking about the sound, just in terms of control parameter. Is she playing the same on all instruments? Because we feel like she will play how she's used to her own instrument, and maybe another instrument, if it doesn't produce the sound that she's used to, maybe she will adapt. Maybe she will play slightly closer to the bridge to get more brilliance because her instrument is very bright. Or maybe she will play slightly with less speed because it's too loud, or I don't know, things like this. So we want to compare how she plays 2 unknown instruments to how she plays her own instrument. And so she had to play a few excerpts Tchaikovsky, Glazunov, Mozart. She has to play as well the best beautiful note that she could achieve, the longest note, arpeggios, different things. And right now we are processing the data. So we have the control parameters, but to actually look at them and see, is it really more different between her violin, between a non-owned violin, compared to what she did twice in a row with her own violin? It's not so easy to tell, how to quantify, and because it's that more, maybe we are by, usually you average over the time of the note, but maybe by averaging, you will actually skip what actually matters. It's the beginning of the note, maybe it's the end of the note. Then we can just correlate along the full, but that means that we need to align, which we have done. But is a correlation, a global correlation, really telling us something that is perceptually relevant? We don't know. So we are exploring different directions, but
Are you going to talk about this next month?
if you want, I can. If we have
You
enough
signed
results
up
by
for
then.
you signed up for March, but you didn't actually tell me what you would talk about.
No, I don't. I still there are many things I could talk about, so I don't know.
Okay,
We'll see.
but you will talk about something next month at this time.
Yes, you asked me to, so I will.
Okay, all right.
I don't know, but I mean, so we thought we had a simple question. We thought we gathered the data, and still it's more challenging than we thought to actually know how to put this data and have an answer to the question we are asking.
Sounds like a familiar progress. Yeah, okay.
Yeah, and I was wondering also, I agree it's really difficult to keep the scientific method until the end of this kind of research, because there is so many variables that come to play. And regarding the perception of bows, we used to say, oh, this bow sounds harshy, or this bow sounds sweet. It's like, regarding how the violinists perceive the bow is through the sound of the violin, and I can't stop thinking that in the same way we describe the sound of a violin with terminology that come from other senses, where the categories are much more established. For example, this violin is warm, it's sweet, or is I don't know, other terms that can relate to taste. When talking about bows, we perceive it, but through the sound of the violin, and we think that we perceive it as, oh, this is a harsh bow, this is a soft bow, but it's also the feeling that comes through the right hand, and the comfort that in this loop that makes us establish these perceptual categories that we use to describe the bows. So it's much more complex than violins, I would say, because we are not only having the auditory perception, but we are also having this haptic perception, and what we are feeling with the music that we are playing, and what we can relate. Yeah, it's really interesting, but really complex perception of these bows.
Yeah, so Victor, I mean, I totally agree with what you said. But there's one interesting thing, though, is that, with respect to the certain bows sounding harsh, my experience is, again, that what the difference is what most people think they are. They're much, much smaller or than people actually think they are. But I'm convinced that there are one or two outlier bows that consistently sounds much noisier somehow. And because they're outliers, I've always thought it would be interesting to do some research on those outlier bows to see if we can actually measure any differences, like with Boeing machines and stuff like that. Just like, it was John Lamacusa, that was his name.
Yeah,
when he
that's
did
right.
the spectral studies with his Boeing machine with different bows, he found all of them were basically that he couldn't tell any significant differences, except for one outlier. I've always wondered about that one outlier bow. What was it about that particular bow that he could measure spectral differences?
And they were heard the same way.
I don't know. I forgot all of the variables involved in
Okay.
that study. I
No,
could try to dig
I
it out, but
suppose.
um,
Yeah, I remember
was-
the study of La Mancusa and the perceptual classification that he made. That was really interesting. But I think he worked with Claudia at some point, and Claudia sent me these sheets where the participants were invited to say from 1 to 10 how harsh is this bow, and from but yeah, I will.
Well, did that ever get published? I
The
know
La
John
Mancusa
gave up on
study,
it.
I don't think so.
And because it was flawed? I mean, did reviewers have problems with it, or did he run out of patience? Or
oh, Jay just raised his hand.
Mm-hmm. Jay, hey.
You're muted. Jay, you're muted.
The PowerPoint presentation that he did in 2013 is on the archives of the acoustics workshop, if you want to look there.
Ah,
Oh, wow. It's like, wow, that was 12 years ago.
2013. Okay.
Yeah.
Yeah,
And
no,
the-
we had planned to publish, we started, and then as many data, you collect them, and then you don't finalize properly the analysis, and then he didn't come back to Oberlin, and then
That's a shame, because that I thought was an important finding. It would be good to have it on
Yeah.
the record. He seemed a little, when I asked him about it, he seemed maybe a little embittered about it, was the difficulty of getting things published. I can certainly empathize with that.
Well, also, hadn't he been working with Norman Pickering a bit on things, and when Norman's health fell, maybe lost interest a little bit too? I'm not sure of that.
It's possible. I mean, it's there was Victor, just for your information, and this is just historical. It's not really of any practical use now. We did have several little private bow working workshops, at least twice at Norman's house. But this was like 15 years, 20 years ago, and so. Unfortunately, 3 of the key participants have since passed away. One was Norman, who passed away, I think, in 2015. One was John Graebner, who got interested in bows, who was a retired Bell Labs physicist. And the other person who just passed away was John Aniano, a bow maker. And so,
Dangerous research.
yeah, and we even had some sessions up at Oberlin as well, on the topic of bows. But yeah, I think once Norman passed away and John Graebner passed away, we lost momentum on that.
Yeah. Then Colin did a few papers that were really interesting, and that sort of
Yeah.
revived things.
Yeah, he was coming from a very theoretical and analytical point of view.
But he was the first one that time I came in contact with a lot of these notions of, bouncing points and just the real, and he laid it out really nicely.
Well, he didn't. He looked at the camber and the and the effects of that and any effects of the modes, but a lot of the actual bouncing characteristics and sort of investigation on the practical aspects of a lot of this was, of course, all done was Knut Gutler did a lot of that, and unfortunately he passed away 12 years ago. So he wrote that the paper that was published in the Catgut Journal, I think, was very influential on the bouncing properties of bows.
So Victor, you're getting your PhD, but you're not off the hook.
Yeah.
I know.
We have all these questions we want answers to.
Yeah, but it's I think that the most difficult part was inviting people and be able to reach to professional violinists for taking the test, and it was a bit hard, but I don't regret it.
Well, you've answered one, it's one little well, it's not
Yeah.
little, but in terms of the big picture, it's only one piece, but it is one important piece. And as you know, when I said that most bow makers didn't know about the moment of inertia, I did not mean to imply that bow makers did not know about the effects of that, which Matt, pointed out that most bow makers absolutely know about the effects of that. But what I meant was that though because they're not, they don't speak the language of physics, they're thinking about the end effects and they know what they need to do to try to control that, but they actually don't know about the actual physics concept of moment of inertia.
Well, if you think about it, human beings have been, waving sticks around and
Right.
for all sorts of purposes for millennia and are really good at it. I mean, our nervous system senses what's happening, if your sword is vibrating or, so
Yeah.
we're obviously really good at doing that. Our brain is
Yeah, they
highly
know the
developed for
effects.
that.
They're absolutely aware of the effects and they have a whole long list of experiences and things they do to try to do the effects, even if they
So
don't
it's
know the
perfectly
physics.
reasonable to assume that their intuitions are based on real things.
Yeah,
It's,
exactly. Yeah.
Well,
Well-
folks, I'm gonna have to take my leave. Very interesting talk, Victor. We
All
want
right,
to
thank
hear
you,
more from
Evan.
you.
So I think, are there any final questions? We should probably wrap it up here, and let Victor go, if he needs to go someplace.
Or buy him a drink.
Yep. I'll still stick around if people, want to talk about this or anything else.
Yeah, I did not. If anybody's interested, well, I did not leave I can leave my mail on the chat. So that's if anyone want to reach to me, they can. Yeah, there we go.
Thank you. Well, thank you so much.
Yeah,
Victor.
thank you so much.
Thank you. It's great. It's great to talk about bows again.